Hello, everyone. In this video, we're going to be looking at section 1.2 and chapter 2 as we continue our curriculum. So chapter 1 gave us a nice overview of a lot of the vocabulary and really what the point of statistics was. And this particular chapter, along with section 1.2, deals with the first part of descriptive statistics, which is looking at variables and graphs. So the reason I take section 1.2 and talk about it with chapter 2 is that it makes a little bit more sense, because once we've introduced the different types of variables that we can have, it just then is a sort of a natural flow of, okay, well, how can we display the data from these variables graphically? And so that is really the motivation for why I have arranged it in this way. So quite a bit of ground to cover. So we're going to look at the different types of variables that we deal with, quantitative and qualitative variables. So a variable, hopefully you remember from chapter 1, is some sort of characteristic that changes from individual to individual or subject to subject, participant to participant in the study. Section 2.1 deals with frequency distributions, and then 2.2 deals with the different types of graphs, and then section 2.3 sort of ties all of this together and says, okay, we put the graphs together, so what? What is the point of this? I will actually try to incorporate elements of section 2.3 throughout the conversation when we look at the various types of graphs. It seems sort of natural to have a conversation about what the graph sort of tells us as we build and look at it. Okay, seems a bit easier in that respect. Okay, so again, do we remember the definition of variable? Do we remember what data, how do we define data? So this is familiar territory, hopefully, from the chapter 1 slides. Okay, so just in case you needed a quick refresher on what variable in a data is. Now, we have a tendency to deal with two types of data, two types of variables. One is qualitative and the other is quantitative. So you have to know the difference. And in a few minutes, you're going to have to know which types of graphs we use for each data type as well. So qualitative data, we generally will call categorical data. Okay. This is where we have sort of labels or descriptions or descriptors, okay, or categories. So it's more wordy in its elements, okay? So your class standing, freshman, sophomore, junior, senior, those would be considered qualitative data because they're technically categories. They're technically labels, right? That is something that we use to sort of put a label on an individual. Now, the interesting thing is with qualitative data, I can't do the regular mathematical operations on them. Okay, so taking, for example, the freshman, sophomore, junior, senior, I can't add, subtract, multiply, and divide them. All right. Now, we do have to be careful because qualitative data can also include things like numbers. Okay, we have numbers that are used as labels. Take your zip code, for example. Okay, your zip code is a label, your social security number, your phone number, the house or apartment number that you have, okay? These are considered qualitative data. Now, you might say, well, can I perform operations on them? I mean, you can, literally, but they don't have a meaning, okay? So for qualitative data, any kind of mathematical operation does not have any meaning. Now, quantitative data, on the other hand, is a bit different. These are things like counts or measurements, okay? And in this instance, I can perform operations on them and there is meaning. So for example, if we look at height, height is a measurement. And if I say we have two individuals, one has this height, the other has this height, I can subtract the two and tell you who is taller and by how much. I can give you a total height, right? I can add them. So there is meaning that goes with that. Okay, so again, just another way of describing qualitative descriptions and labels, quantitative counts and measurements. So make sure you are familiar with this. Okay, what I would suggest you do is pause the video and give this set of examples a try as you classify the data as either qualitative or quantitative. This would be a wonderful exercise for homework, test, and the final. All right, part A is asking us to look at shades of red paint in a home improvement store. So there are a lot of shades of red paint in a home improvement store. So if you haven't been to the store to see that, there is quite a few. So anyway, all right. So, is it qualitative or quantitative? Well, paint colors themselves are labels, right? Categories. So this would be qualitative data. Part B is asking for the rankings of the most popular paint colors for the season. So a ranking. So most popular, next, second popular, third most popular, fourth most popular, and then not popular. So giving each of those that title, that would also be considered a label. So that would be qualitative data. Now, if you said, well, rankings I think of as like 1, 2, 3, and 4, those are still labels that we are associating with, right? That's still a label that we are assigning. First place, second place, third place. So still qualitative data. Part C says the amount of red primary dye necessary to make 1 gallon of each shade of red paint. Look at the first word, an amount. Okay, an amount is a quantity. Okay, that sounds like a quantitative variable. An amount is a measurement, so some measure of volume. Perhaps it's ounces or milliliters or liters, half of a gallon, a pint, whatever the measurement is for the amount. So that clearly would be quantitative. Part D says the number of paint choices available at several stores. So the numbers of paint choices. Okay. Well, if we consider, let's say, Lowe's, Ace Hardware, Home Depot, okay, and we put numbers on each of those stores for what they have available, sounds like that would be considered a count, okay? And since we're dealing with the number of paint choices per store, we're measuring it in that way, that would be quantitative data. Now, within quantitative data, we also consider something called continuous and discrete data. Okay, this will come back to us in section 5.1 and in chapter 6 when we look at discrete variables and continuous variables. Continuous data are quantitative data that usually take any value in a given interval and are usually measurements. Okay, so something like a height would be considered continuous data. One, because it's a measurement, and the second is because I can have fractions, decimals, etc., with a height, right? I can tell someone that they are, I don't know, 6.1 feet tall or 5.8317 feet tall, right? I can use various decimal values or fraction values. Okay, so continuous, we think of it in that kind of way. Discrete data, on the other hand, this is where we take on very specific values, and they're usually counts. We don't deal with fractions necessarily. So if I wanted to know the number of homes in a particular set of blocks in a neighborhood, that would be considered discrete data. If I was looking at the number of people enrolled in the various Stats 1020 classes, this would be considered discrete data. I can't have a fraction of an individual. That does not make sense in those instances. Okay, so there is a difference between them. So we have to make sure that is clear. So again, quantitative data, we break down into discrete and continuous. If you're reading the book, they actually break this down a bit more into various levels of measurement. You're not responsible for knowing the levels of measurement for this class, but that information is in the textbook, and you may see that come up in other statistics courses. So if you want to pay attention to that, you're certainly welcome to. This exercise asks us to determine whether the data here are continuous or discrete. So why don't you pause the video and give this one a try? All right, let's see how you did. So part A says the temperatures in Fahrenheit of cities in South Carolina. So temperature is a measurement. So this has to be continuous. Okay. Temperatures are indeed measurements. Part B, number of houses in various neighborhoods. So I think we kind of talked about this one a few minutes ago. So this would be discrete as it is a count. Same thing with part C, the number of elliptical machines, right? I can't have fractions of a house, fractions of an elliptical machine. So B and C would be discrete. And the heights of doors would be continuous because a height is a measurement. Now, that kind of overviews the section 1.2. That was from chapter 1 about the two types of variables. We move now into section 2.1, and this deals with frequency distributions. And there's a series of definitions that are on here. Okay, so I'll touch on each of these. So A frequency distribution, you're going to see the word distribution a lot. Distribution really sort of says that what we're doing is we're displaying what the variable is sort of doing. And I know that's a strange sort of definition, but we've got different types of distributions that we look at. A frequency distribution, in a moment, you're going to look at, or not in a moment, but in a couple of weeks, you're going to look at probability distributions. You're going to look at the normal distribution, the chi-square distribution. So there are lots of different types of distributions, and they're showing us these ways in which the variable can take on various values. Now, a frequency distribution is used to show us two things. One is the values the variable takes, okay? And the second is how often they are taken. That's the idea of a frequency. Frequency means how often something happens, okay? So you might hear someone say, what's the frequency of vehicles entering the parking structure number 2 at Wayne State University on a Monday? Okay, let's track it by hour. All right, so the variable here would be each of the hours, and then somebody would count the frequency, the number of vehicles that come in between 7 and 8, 8 and 9, etc. Okay, so again, what is a frequency distribution? It shows us, number one, the values the variable takes, and secondly, how often they are taken. In other words, the count. Okay, and that's what a frequency is. It's a count. Okay, numbers of data values in the categories in a frequency distribution. That's a more technical definition. It's essentially a count. Now, a class, they're calling a category of data. It's almost like a range, okay, a range of data values. And so we define how wide it is with something called the class width. So in a frequency distribution, sometimes we want a range of values to count, like I just did 8 a.m. to 9 a.m., 9 a.m. to 10 a.m., 10 a.m. to 11 a.m. The width there would be 1 hour. Okay, so that's how we would define the width, the lower limit subtracted from the upper limit. And then we have something called a relative frequency. And we'll talk about this in a moment. This is where we build some fractions and percentages from those fractions. And I'll show you how that will work in a moment. But you've got some of the technical terms here listed. Okay, so let's try to build a frequency distribution. What we have on the screen are TV prices, and thankfully they're in order from least to greatest, okay? So the TV prices range from $1,595 all the way up to just shy of $2,000. So what I want to do is build a frequency distribution for this data, and I also want to capture what the relative frequency is. So what I'm going to do is I'm going to define the classes, in other words, the range of prices, to be $1,000 each. So from $1,500 to $1,599, okay, is roughly $1,000 if we count that 1,500 as one. Okay, I know that sometimes is tricky for people. I say, is it the difference $99? Well, technically it's 100, right? Or 1,000. 1,500. No, yes, 100. I'm sorry, 1,500 to 1,599. That 1,500 we count as number one. Okay, so these are $100 increments. So 1,500 to 1,599, 1,600 to 1,699, etc. Then what we do is we go through and we have to count how many prices are within each range, okay? So how many TV prices do you see between 1,500 and 1,599? With these being in order, should be very easy to see. There are two, 1,595 and 1,599. How many in the next class? That should be 5, 1,685, and then there are 4, 1,699. So you continue in that way until you've captured all of them. So how many between the 1,700 range? That's 4. The 1,800s should be 5, and then 4 for the 1,900s. Okay, so what you're looking at there is the frequency distribution. If we add one more column, we get what we call the relative frequency, and that's what we'll talk about in a moment. So first of all, I want you to notice the values the variable takes. That's considered the class here. And how often they are taken is the frequency. So those are the two things that the distribution shows us. Now, in order for us to get the relative frequency, what we need to know first of all is how many TV prices are we looking at? And the answer here is 20. And on the previous slide, we called that the sample space, or n. So that's going to be the denominator for every single one of these fractions that we are going to build. Now, the question is, what percentage or what fraction of the TV prices are between 1,500 and 1,599? And the answer to that is 2 out of 20. How many, or what fraction rather, are between 1,600 and 1,699? And the answer to that is 5 out of the 20. So when we simplify these, we indeed come up with a percentage. So 2/20 simplifies to 1/10 or 10%. 1,600 to 1,699 is 25%, and you see the remaining ones there. You know you did this right. When you sum this, the percentages, you get 100. Okay, that's how we know we got it. Similarly, the frequency should sum to 20. Okay, and that's how you know you got that right, because there are only 20 prices in the table. Now, relative frequencies are going to come back to us in a few minutes because we use them to help us to build together another type of graph, which we'll look at in a moment. Okay, so what we're going to look at now is getting ourselves into section 2.2, and we're going to look more specifically at qualitative data and the different types of graphs that we can make. And really there are two. We use a pie chart or a bar graph. Okay, pie chart or bar graph. So these are the two you will be responsible for. There certainly may be more or variations on these two graphs, but these are the ones that you'll be responsible for. One, being able to create from scratch, and two, being able to provide some kind of analysis to. Okay, so again, qualitative data provide us with a view of categorical or labels of specific traits. Now, some graphing advice, very important. Number one, the graph should be able to stand alone from the original data. Okay, what this means is you don't need to present everybody with the long spreadsheet of data values that you used to make the graph. Okay, the graph should be 100% something you should be able to put on a PowerPoint slide or poster or embedded in your paper without the original data. Okay, we don't need to see all the pages of that. The second, and the one that most of you will forget, is that every graph you produce for me must have a title and labels for both axes, if we have axes. Okay, so you absolutely need to have title and labels. Very, very important. A number of you will forget these details and then we'll be arguing points with me, but there is no argument because these are things that are essential for the graphs. And number three, when appropriate, sometimes we may need a legend or a key. Okay, those things are helpful, especially if we have different colors. Okay, a source is always good to include if you have one, and then a date that maybe goes with that source. So, for example, if you were collecting data, maybe a quick survey, someone's favorite restaurant or something like that, just standing outside the classroom as folks enter, and you write that information down, then a date of when you capture that information, sort of similar or in tandem with the source. Okay, so how do we label things properly? So again, a title. Okay, make sure that we have bar titles that go with that, and then a picture of what the source would look like from a particular graph. Now, sometimes, depending on the citation manual that you're referencing, depending on your discipline, they may have certain rules that you have to follow for how sources are to be cited, those sorts of things. Okay, so right now we are not going to be elaborately picky. Those things will be ironed out in your future statistics classes that you take that are more centered on your major, etc. Okay, but anyway, this is at least an example for what those things should look like. Okay, so let's look at pie charts. These show us how large each category is in relation to the whole, and that's really the whole idea, no pun intended, about using percentages. Okay, and as a matter of fact, we actually use relative frequencies. Remember when I said a few minutes ago that's going to come back? Here it is. Okay, so relative frequencies are useful for pie charts. Okay, so there's conversation here in this paragraph about using the angle measure of 360 degrees to figure out, how many degrees do we need in order to slice up the pie. You're certainly welcome to use that if you wish to. Generally, we can do this freehand. And I can demonstrate this for you in class. As long as it's reasonably close, that's fine. And some people may also want to use statistical software. Microsoft Excel, for example, can create the graphs, and that's perfectly fine too. If people want to do it freehand, that's fine. We can talk about that in class. So this is the information about relative frequency that you've seen a few minutes ago. Again, that's going to come back to help us to build the percentages here, okay? But this is essentially how we get the percentages for a pie graph. We are looking at relative frequencies. So when you see that phrase relative frequencies, really saying is we need to think fractions. Okay, so our job is to create a pie chart for housing types of students in a statistics class. So we have a grand total of 49 students, not 490, 49 students. And they're broken down in apartments, dorms, a house, and in a sorority fraternity house. And so you see the numbers here. So what we need to do is, first of all, figure out what the relative frequencies are. So for apartment, we would need to take 20 out of 49 and figure out what that percentage is. For a dorm, 15 out of 49. For a house, 9 out of 49. And for the sorority fraternity house, 5 out of 49. And so that's what this slide is showing you, each of those relative frequencies. Now, you'll notice that it's using the approximation equal sign. 20 out of 49 is about 0.41, which is 41%. If we end up getting something like 100.03% or 99.926%, good enough. Okay, we understand that there'll be a little bit of rounding that's going to happen with the fractions, et cetera. So as long as we are as close as possible to 100% above or below, we are okay. All right. Now, obviously, apartment has the bigger percentage with 41. Dorm is second. House is third, and then the sorority fraternity house at 10%. And so, again, using some statistical software, this is what the graph would look like. And you'll notice, number one, we have a title, okay, that's nice and bold. The percentages are labeled, and there is the inclusion of a key, okay? I suppose you didn't necessarily need one for this graph. We could have put these labels on the bar, not on the bars, but on the pieces themselves. That would have been okay, or maybe off to the side. It's a matter of preference. I don't think we lose anything by having the key as it's presented here, but it makes it easy to see which of the categories here, okay? All right, so as with all the graphs, the question we will ask is, who cares? Okay, what does this tell me? Is there anything that is particularly important in this respect? And the answer to that question is, well, it's going to depend. It depends on who's looking at this, who the audience is. If I were a housing administrator for the university, I might be a bit concerned because I see a lot of students are living in apartments. Okay, and I might be wondering, well, why? Why is 41% of students living in houses? What's going on here? Perhaps it's or apartments rather. What's the issue? Is there a cost problem? So maybe I need to lower the rates for dorms, okay, to try to get that number up a bit more. So again, it's going to depend on who the audience is. So 4 categories here, not anything earth-shattering. Now, we can also use bar graphs to represent qualitative data as well, okay? And there are 3 different types of bar graphs that are here: Pareto charts, side-by-side bar graphs, and stacked bar graphs. So the last 2, side-by-side and stacked, are nice when we are trying to compare the data from same categories, but for different groups. So for example, maybe I'm looking at the housing types from this year and last year. Okay, so what percentage of folks did apartments from this year to last year, right? That's a side-by-side sort of comparison. A Pareto chart is a bar graph, but we put the bars in order, okay, in descending order. So we'll take a look at that in just a moment. So we're going to return to the same data that we had a moment ago, okay? And this time we're going to use the bar graph. Now, the good news for the bar graph is that we do not need to compute any percentages. We simply report what the counts are, okay? Let me go back for just 1 second. If you look at the number of students, does everyone see how this ranges from 5 to 20? How you decide to break up your y-axis where it says number of students is going to depend on what the counts range from. So somebody could have easily went up by 4 if they wanted to. Obviously, the Hawks decided to use by 5s, which I think is fine. We don't lose any meaning or anything like that here. A couple things to point out. Number one, we have a title for the graph: housing types for students in a stats class. We also have labels. You see how it says type of housing on the x-axis? So we know what an apartment, dorm, house, and sorority fraternity house is. And you notice that the numbers 5, 10, 15, 20, etc. are labeled as the number of students. So it's very clear what we are looking at. A couple of other features for the bar graph. Notice the bars are not touching. We leave gap. Okay, so very important on a bar graph, we leave gaps. Why do we do this? To make it easy to read. Okay. Now, the other thing you're going to notice is that the bars here are in descending order. This is called a Pareto chart. So this is a bar graph, but it's also called a Pareto chart because it's in order. Now, similarly as the pie graph, we put this nice graph together and we ask the question, well, who cares? Okay, what does this tell me? All right, well, it gives me the counts. All right. And again, if I'm a university official, I might be concerned that we've got students who are using apartments as the most popular housing type, and maybe I need to do something or figure out some incentives for increasing the dorms. Okay. Now, in terms of which graph is most appropriate, the bar graph or the pie chart, that really is going to depend on the story you want to tell. All right. Personally, I think we get a little bit more out of the pie chart than we do the bar graph. But again, it's going to depend on what sort of perspective we wish to discuss. If I just want to report what the counts are, then using a bar graph is a better measure for that. Now, on the quantitative side, we have a couple of different graphs that we use, histograms, stem and leaf plot, and line graphs. Dot plots are there too. You won't be responsible for making a dot plot. I do mention it because it is discussed in the book. There are certainly others. There are a couple that we're going to get to later on in the semester. One is in chapter 3, the box and whisker plot, and then the other is the scatter plot in chapter 12, much later in the term. So we'll add to that list, but there are certainly others as well. For the purposes of the exam final homework, histogram, stem and leaf plot, and line graphs, in addition to the pie chart and the bar graph, was what you'll be responsible for being able to, number one, construct from start to finish, and secondly, being able to interpret. Okay. The graphing advice, did you all remember reading that? It's the same. Okay, so that hasn't changed. So I have to repeat it again, even though it's a new set of graphs. All right. This you should have remembered also from the qualitative discussion, how to properly label a graph. Nothing's changed. Okay, so definitely make sure that we have a title. There are labels for the axes, the source, etc. Okay, so the first type of graph we're going to look at for the quantitative side is known as a frequency histogram. Generally, we call it a histogram. Okay, this technically is a bar graph, but it's a bar graph of the frequency distribution for quantitative data. So what this means is that we first use or build the frequency distribution, and from the frequency distribution, we're able to make a histogram. Okay, and a histogram shows us frequencies. Okay, frequencies. There's also something called a relative frequency histogram. This is where the heights of the bars represent the relative frequencies. In other words, the percentages. So our focus is mainly on the frequency histogram, but some of you might see relative frequency histograms in your work. So again, it is a bar graph of a frequency distribution. The horizontal axis, that's the x-axis, represents the number line. Okay. And the reason is because it's going to be broken up into the classes. Do you remember the class column on the frequency distribution that we did? Those ranges of prices for $100 width, okay, for the TVs. That's the idea. The width of the bar represents the class width from the frequency table and has to be uniform. Not should be, it has to be uniform. We do not have these as different sizes. The bars in the histogram should touch, so we don't leave gap in histograms. Bar graphs we do, histograms we don't. They are tightly packed. Okay, they touch. And the height of each bar represents the frequency of the class it represents. So the y-axis is going to represent the count. Okay, that's where the frequency lives. All right, so what we're going to do is create a histogram for data that's going to be on the next slide that shows the percentage by state of residence 65 and over. So how do we make a histogram? So the first step is to divide the range of the data into classes of equal width, okay? So these are by percentages. So the question is, how wide do we want to make the percentages? That's going to depend on the range in the data, and I'll explain that in a minute. The second thing you do is you count the number of individuals in each class. So step 1 and 2 is really building the frequency distribution. That's really what steps 1 and 2 are doing. Once we have that, we can draw the histogram. Okay, so here's the data. Now, what we're looking for here is to see, okay, what is the lowest percentage? I see 7.3% as the lowest. And the question is, what is the highest? And let's see, I think Florida is the highest. No surprise there, 17.4%. So we have 7.3 to 17.4. So that's almost a 10% range, okay, for how wide it is. So the question is then, well, what should we break up the frequencies into, the classes? And I think the suggestion that we used is 1%, and that'll be taken care of here on the next slide. So it is easier to construct the frequency distribution first, which is what we're going to do. Here it is here. So each class you see ranges from 7 to 7.9. So again, if we count 7 as the first, literally the first number, these are 1% wide, 7, 7.1, 7.2, et cetera, up to 7.9. So it's a 1% width. So that is why we have, let's see, 4, 8, 9, 10, 11 of them, okay? And then what we do is we count the number of percentages that we see that fall within these ranges. Excuse me. Now you'll notice that we have two classes, 8 to 8.9 and 16 to 16.9, that have a count of 0. So I want you to remember that when we look at the histogram. Okay, so here's what the histogram looks like. So first of all, you'll notice between 8 and 9 and 16 and 17 that there is a gap. That represents that we had a count of 0. Okay, we had a count of 0. So the only time you have a gap with a histogram is where we have a count of 0. Okay, a count of 0. Let me go back for just 1 second, because what I want to focus on is the y-axis for a minute. You all see the number of states and how it goes up 2, 4, 6, 8, 10, etc. If you look at the counts range from 0 to 19. 19 is the highest count. So the question is, okay, 0 to 19, how should we break up the increments? And so it made sense here, I think, to do by 2, because some of the numbers in the counts were a little smaller. You could have certainly done by 4 or 3. That would have been all right. 5, I think, would have been a little bit too much, at least to try to read this a bit accurately. So I think 2 is fine. Sometimes you have to play with the scale. Okay. Now, if you look very carefully at this graph, it's missing something. Did you all notice? It is missing a title. Okay, so you got to make sure that you put titles on the graphs. Very, very important. Now, the question is, we look at this and say, okay, well, who cares? What's the observation that we have? Well, if you notice, between 13% and 14%, that's the tallest bar. So most of the states, 19 of the states, have percentages of 13 to 14% of residents who are 65 and older. So that's one way we can interpret this. And if you notice, there's some left counts, 7 to 8%, 9 to 10, and then 17 to 18. We call those sort of the tails, and we'll get into the idea of shapes of the graph in a moment. But those would be considered the special cases, or maybe even the outliers in the graph, right? So what state has between 17 and 18%? Interesting, right? Obviously that was Florida. And then, oh, there's one on the lower end, 7 to 8%. I wonder what state has that, right? And that was Alaska. And makes sense. Not many people travel to Alaska. And certainly a lot of the folks 65 and older, right, they sort of retire and do a lot of traveling down south, Florida in particular. All right, so constructing the bar, just like bar graphs, constructing a histogram is a process that we have to think about in some detail. And the reason is because these bars are something that our eyes have a tendency to respond to. So a couple of pointers here. We want to make sure that the classes of the histogram have equal width. So the one we used a moment ago was 1%. Now the question is, how many classes should we have? And the magic number is somewhere between 5 and 15. So on the previous graph, I think we had 11 total from the frequency distribution. If you have too few classes, what happens is most of the data gets bunched up into the bars, and then they look super tall or like skyscrapers. If we had, let's say, 30 classes, then the graph would just be really, really flat, okay? And it would sort of give a pancake impression. So sometimes when you make the histogram, you have to play with the number of classes. So sometimes you have to have one or two histograms and kind of compare, okay, which one is the best. Statistical software certainly enables us to remove the idea of thought from that. I have used Microsoft Excel a little bit as well as SPSS, and even with that, there's still some adjustment that you have to make to get the graph to kind of feel right, where the classes seem a bit more reasonable. Okay, with histograms, we also like to have a tendency to describe them in terms of their shapes. So these are the 4 shapes that we can assign to histograms. So you will need to know these. We will have to apply them in some sort of capacity. Okay, so this will also have implication in chapter 3 when we deal with the measures of center. Okay. Now, we also have one other feature of a graph that it could potentially have, and I mentioned this already, and that's known as an outlier or outliers. These are data values that lie outside the main group of the data. They stick out very much so. We can tell where the outliers are. It would be almost like everybody doing very, very poorly on an exam and that 1 or 2 people who do really, really well. And of course, vice versa. Everybody does really, really well. And we have 1 or 2 people who do not do as well. Those folks who are not with the majority are considered the outliers. Okay. All right, so let's look at the shapes of graphs. So first of all, this is a histogram, and you'll notice that there is a red line there. Hopefully you can see that. And the red line is going horizontally across the page at about 70. This is what we would call a uniform distribution. It's practically flat. Okay, someone might say, well, it's not exactly flat. Well, it's approximately flat. So uniform here means that the frequency is about the same for all of the classes. Symmetrical is pretty self-explanatory. Quite frankly, the graph that we built with the percentage of folk 65 and older was a symmetrical graph. Okay, sometimes it's not quite symmetric exactly, so you'd say it's approximately symmetrical, and that's perfectly fine. We get the idea. It's not going to be perfect. We're just describing the shape more generally. We can also have a graph that is skewed to the right. Now, this is generally hard for folks to get straight because they confuse it with skewed to the left. You'll notice that there's a bunch of tall bars on the left side. That's where most of the data is located. You'll notice on the right side, those bars are very, very short. That's called the tail, okay? Because the tail is on the right side, we say it's skewed to the right. All right. This would be the example where a whole bunch of people do really, really bad on the test, and we have a handful of folks who do really, really well. That's a right skewed or right tailed or skewed to the right distribution. So skewed to the left is the other way around. Okay. The tail is on the left side. Okay. So again, we call this skewed to the left skew distribution. Skewed left distribution, just something to indicate that it's a left skew. So again, it's where the tail is. Where is the tail? It's on the left side, so it's left skewed. In this instance, all the data is on the right side, most of it with the taller bars. Okay, so if we could describe the shape of this distribution. I hope you said symmetrical. Okay, that is definitely symmetrical. This one is an interesting example. The claim is that it's right skewed, but do you notice that between the 99.5 and the 104.5, there's an outlier? Okay, so the outliers can, impact these kinds of things. So people might ask, well, what do we do then if we describe the shape? I would say, if I was writing this up in a report about the test scores, I would say we had a symmetrical distribution here, but we had one single outlier. That's it, one single outlier. It's not like we had other scores that were between 89.5 and 99.5. There was just one single outlier here. The other type of graph that we can build is a stem and leaf plot. And these are very similar to histograms. And what these do is they actually retain all of the original data. In other words, I can see every single data point in a stem and leaf plot. On a histogram, we can't, right? They're all bunched up into the classes. Now, the leaves are usually the last digit in each data value, and the stems are the remaining digits. And you have to have a legend or key to accompany this so that we know how to interpret the information. That is essential in these, and we'll look at an example in a moment. So to construct a stem and leaf plot, we have to create two columns, one on the left for the stems and one on the right for the leaves. And we list each stem that occurs in the data set in numerical order. And each stem is usually listed once, okay? Sometimes the stems might be listed twice, depends how much data we have and if it displays the data a bit better. So in our cases, we generally list them only once. Then next to each of the stems, we have to list the leaf, and the leaf is listed as many times as it occurs. So repeats are included. So you have to make sure you write the repeats down. Okay, you do not exclude them. And we make sure that we get them all lined up. And of course, we create a key for the interpretation. All right, so it says, if desired, put the leaves in numerical order, and it says to create what's called an ordered stem and leaf plot. And you see my parenthetical there. You are to do this, so you need to make sure that the leaves are in order. So let's look at an example. So we have a stem and leaf plot that we're being asked to create for the ACT scores for a group of college freshmen. Okay, so we have 18, 23, etc. Now, if you look carefully, the lowest score here is 17, and I think it goes up to something to 35. Okay, so 17 to 35. So the stems have to do with what the first digit is. So the first digits for these scores would be a 1, a 2, or a 3. Hopefully that is obvious. Okay, and then the leaves would be the second digit for each of the numbers. So the stem and leaf plot would look like this. So let's make sure that we understand this. So the first value was 18, and I hope you see that the stem is 1 and the leaf here is 8. And if you go across the first row of data, the next one would be 19. That's why there's a 9 listed next to that. The next one would be 18. That's why there's an 8 listed next to that. Then there's another 18, which is the 8, and then the 7. And then this process would repeat for the 2 and the 3. So if we pick on, for example, 29, okay, that is listed right here, stem of 2 and a leaf of 9. Obviously, there were other values that came before it. Now, if you look carefully at the stem and leaf plot, you'll notice that the numbers are out of order, so we do need to put them in order. And now we have an ordered stem and leaf plot. You'll notice that we label the column stem and leaves. We have a title, ACT scores, and more importantly, a key so that somebody knows how to read this. And what you also should notice is we have all the data values listed. So I could count each one of the leaves, and that would tell me how many scores we have, which should be 20. Okay, now here's another set of data that we're going to be asked to create a stem and leaf and plot for. And what you should notice here is that we have to treat this a little differently. And the reason is because all of the digits, the last digits, end in 0. And as a matter of fact, the second to last digit also ends in a 0. So it'd be a very boring stem and leaf plot. So what we have to do is actually use the first 3 digits of each of these salaries only, okay? So the stems are actually going to be the 51, the 48, the 40, the 40, the 48, etc. And the third digit is going to be the value we use in the leaf. And that's what this part here explains, okay? So if we had, for example, 40 line 7, we would interpret that to mean $40,700. Okay, so $40,700. So those zeros we exclude because it's not going to be helpful for us in putting together the stem and leaf plots. So as a result, we account for those last 2 digits of 0 in the key. Okay, so it's just a different representation for this. Now we have some questions, follow-up questions, make sure that we know how to read and understand stem and leaf plots. So part A asks us, what were the smallest and largest salaries that were recorded? Well, the smallest salary is going to be in the $40,000 range, and specifically 40,700. That's the smallest leaf. And the largest salary, the stem is 51, and the digit there is 5, so 51,500. Now, which salary appears most often? So what you have to do is you have to study the leaves and you have to see which digit is repeated, if any. And I see 2 3s, which would imply $46,300 is the salary that appears most often. We would call this the mode. I know we're getting ahead of ourselves. That comes up in chapter 3, but that would be considered the mode. The next question says in part C, how many salaries were in the range of 41,000? Well, 41,000 is right there. I don't see any, so that's a 0. And part D wants to know which salary range did the most salaries lie? Okay, so there are the 3 ranges that we were provided with. And it appears that the salary range of 45,000 to 49,000 did have the most salaries. You can count the number of leads there to verify. This slide has the exact answers to what we just discussed. We've also got dot plots. I'll leave that to you to read. And we also have line graphs. And this is the last one that I want to focus on. So line graphs are particularly useful for showing things over time. Sometimes we have a tendency to call them a time series sort of graph, shows us things over the time. And what we do is we have the horizontal axis, the x-axis representing the unit of time, months, years, decades, centuries, seconds, whatever. And the vertical axis is whatever we are measuring. Maybe it's a price, okay? And what we do is for each of the points that get plotted, we use straight lines to connect them. That's the idea here. And line graphs are very useful for showing trend, We're going to look at the consumer price index to see the average price or average change rather in value over time for a basket of goods and services. So this is the data that we have from 1920 to 2010. And the CPI for each of those years. Okay, so let's see what our graph would look like. So what we would do is the x-axis we would break up in terms of the year. And this one's kind of nice because you notice they're already broken up into 10-year increments, makes life a lot easier. So that's easy to label. And the CPI, you're going to notice ranges from 14 to 218. So you need to determine what kind of axes you want to break that up into. It might be easier to go up by 25 since we have 218. Okay, maybe 50 increments of 50. That might be a little tougher to graph some of the smaller CPIs. But you see the dilemma that we have, right? That's quite a range. So maybe increments of 25. We'll see on the next slide what Hawks did in a moment. So what would happen is we would need to plot each of these as an ordered pair. So you'd look 1920, comma 20 for the CPI, put a dot, then you do 1930, 16.7, put a dot, and then connect those two. So this is what the graph would look like. So they chose to use for the CPI 50, okay? Couple things, you'll notice again the axis labels, year and CPI, as well as a title for this particular graph. Okay, as with anything, we ask the all-important question of who cares? What does this exactly tell us? All right, well, looking at the CPI, if somebody asked you to sort of describe what the general trend is, I hope you all would agree that it's going up. Okay, now there is an interval of years where it's going down, and that would be between 1920 and 1940. And so if you're a historian and you're trying to figure out what's going on with the CPI, you may recall that we have the Great Depression that we're going on, and there was a gradual decline. Now, someone might say, well, what happened from 1940 to 1950 that caused it to go up? You say, well, you know, we came out of World War II and industry and things started to pick up sort of at a rather slow pace from 1940 to 1970. And after 1970, it really started to pick up, right? That rate of increase went up. How do I know that? Well, the line is more steep. Okay, and so somebody might ask, well, what happened after 1970? Well, maybe there was advancements in trade and trade deals, et cetera, that helped with the consumer price index. Some other things about analyzing graphs. Big note here, make sure you pay attention to these. Okay, so we have a couple of different types of graphs. Time series is one we just looked at. It is a line graph, but again, it's looking at values and how they change over time. Cross-sectional graphs display information collected at only one period in time. That could have, quite frankly, been the bar graph that we looked at, if you remember from a little while ago, that had the various housing types. Okay, that can be considered cross-sectional graph. Maybe we collected that data at the end of a school year, et cetera. And then we have something called a pictograph, which is, yeah, they're bad. Here's an example of a pictograph. This says correct pictograph versus incorrect. I'm gonna be honest with everybody. I don't use pictographs. They're just not good. Okay, a couple of issues with them. First of all, I'm not exactly sure what the top of the house we're calling where we get the count for housing costs. Is it the chimney or is it the peak? It's just not good. They're very misleading for people. So I would strongly encourage you to avoid pictographs in general. They're just not good. A couple of other things for the graphs. Make sure that graphs are scaled properly. Okay, scale has to do with your X and Y axes. So that can certainly impact the shape of the graph very much so. It can shrink it and it can certainly stretch it. So we have to be careful of that. Um, Lines that rise gently on one scale can certainly be very steep on another. There are a lot of people who will play with the scale of the graph in order to make their point across. If I want to really show that tuition has gone up at the university, I might use a very, very small scale where the increments are very, very small, and that's going to really stretch it out. And I'm going to show you that graph, and you're going to say, oh my goodness, did that tuition go up like crazy? But if you look at the scale, you might say, wait a second, you have very small increments there. Okay, so we have to be careful. So if you are analyzing graphs, first thing I would look at is what the scales are. Make sure that they're telling the right story. Here is a graph, a line graph. And the question is, what errors can you find? Okay, that are going on here. Well, there are quite a few. If you look carefully at the x-axis with the dates aren't equal increments. Okay, it's also very cluttered, very difficult to read. They have too many dates that are on there. Okay, so we need to change that a bit. So you got to make sure that the scale is appropriate. And I don't know that I would necessarily need all of those particular dates as well, but you get the idea. Is if we include all this, it really stretches out the data here, right, for the federal hourly minimum wage. So yeah, so some issues there with the scale. All right. Good news is that concludes the overview for chapter 2. What's coming up next will be chapter 3.